Hello, everyone. Thank you for coming. So my name is Jesus Camacho Rodriguez. I'm an engineer at Hortonworks, and I'm going to be talking today about the work that we've been doing to introduce materialized views in Apache Hive. So just let's start with a little bit of an overview, because we've come a long way. So the initial use case for Hive was batch processing. So back then, when it was open source, it was very different. It was only data that you could read. You wouldn't support SQL standard. It was a Hive QL, so SQL-like query language, and you could only execute your jobs using MapReduce. And then at a certain point in time, there is an effort to take Hive beyond its batch processing roots towards more of a kind of an interactive SQL query system that started in Hive 0.10, so beginning of 2013. And yeah, we've come a long way. Latest release is Hive 3.0 that was released last month. And this renovation that took place, it was to improve 3 different axes. One of them was latency. So as I mentioned previously, allow interactive and sub-second query response time. Another one, scalability, so moving from terabytes of data to petabytes of data. And also the SQL support. Move from this Hive query language to SQL standards, so Hive could interact with other applications in a much easier way. Now, during this this period, there have been a lot of internal improvements. So we move away from MapReduce, and now there is support for multiple execution engines such as Test or Spark. There has been a lot of work in implementing more efficient joint execution algorithms for Hive. Also, vectorized query execution was introduced that is very useful for LLAP kind of workloads where you basically execute the same operation on batches of columns instead of on rows. Together with that, integration with columnar storage formats, so org, Parquet. Another huge development, LLAP, so persistent daemons for low latency queries. There was also a lot of work to introduce and improve a rule-based and cost-based optimizer. Together with that, work to improve statistics, because those are the ones, that's the fuel for the optimizer, and you need better statistics in order to basically create better plans, execution plans. And also tighter integration with other data processing systems such as Druid that cover kind of other use cases, and they are useful to accelerate certain kind of workloads. But something that we keep on seeing is that when users want to accelerate query processing, what they try to do is optimize based on access patterns, right? So, for instance, you will have your data in Hive, and then depending on your query workload, you may, for instance, create replicas or copies of your original tables where you, for instance, change the physical distribution of the data, right? So you distribute it by a certain key, or you sort it, or you partition it. Another kind of optimization in that, I mean, based on access patterns, is also filtering rows, right? So you have like a huge table, and you know that you are gonna query only subset of it. So maybe you create, another table that only contains part of the original data. Some people also, very common use case is denormalizing the database. So for instance, if you have a typical star schema, you have a fact table and some dimension tables, you may denormalize this database so you avoid basically running joins when you're running your queries. And finally, another clear example, especially with Druid, is pre-aggregation. So you may group by different dimensions and aggregate different metrics if you think that you are going to be doing those kind of queries. Now, when you go into that direction, the problem in Hive or is that things get complicated very quickly, right? So basically what you are doing is establishing a relationship between the original tables and the new tables, but there is no support for, there is no semantics that are transparent for the system, right? So you cannot answer easily questions such as, has a similar table already been created? Or can I use, another table that was created to answer the same kind of queries? Well, each time you will have like new tables, you may have to rewrite your original queries, right? So you may have to go to your scripts and then suddenly you have to point to a new table instead of the old ones. What happens also when access patterns change? You will also have to scan all your scripts and change your queries, the queries that you are executing. Your users will have to do that. And also, it becomes complicated to maintain your new tables when the original tables change. Most of the times what you will end up doing maybe is rebuilding completely the new tables, right? So we can do better than that. And that's where materialized views come in. Materialized view is not a new concept at all. It's been implemented in database systems for the last 30 years. A materialized view is just an entity that will contain the result of evaluating a query. And the important property here is that suddenly you will expose the semantics of the materialized view to the optimizer, right? And the optimizer can take advantage of this. And yeah, also the system, because you expose these semantics and these relationships between the materialized view and the tables, will be able to do things such as incremental view maintenance. Today I will be talking about materialized views that are created explicitly, but materializations are created in the system in different ways, and the concepts apply one way or another. So you may create them explicitly with the create materialized view statement, but also you may have a daemon that, for instance, scans the last day, the logs looking for the queries that have been executed, and may create a materialized views or materializations based on that. Or it can be even more immediate, like a cache result of a previous similar query. And also even within a single query, right? You may have part of the query that actually can be reused by different branches within the query itself. So that's like an internal materialization. And yeah, in Hive, this is an example of workflow that we kind of envision that you could do with Hive and Druid. So for instance, you may have some Hive tables and you want to accelerate certain workload. So you will create a materialized view that is stored in Druid. And then the user or a dashboard may send queries to Hive. The queries will be referring or pointing to the tables. They don't have to do anything, and Hive will automatically rewrite these queries using the available materialized views, and it will execute the rewritten query. So that's an example of possible workflow using materialized views in Hive. And this is what I will be talking about today. That is what is included in Apache Hive 3.0 for materialized views. I will be, there is. The implementation has the possibility to use different storage options, as I said, so you can store your materialized view in Hive, or you can use other systems that are supported by Hive, such as Druid. I will be talking about the automatic rewriting of incoming queries to use these materialized views and what is supported and what not. I will be talking also about what we have done with respect to view maintenance. And finally, the multiple options that there are that are present today in Hive in order to control the materialized views lifecycle. So let's start with the management of materialized views in Hive. So what we did is just introducing a create materialized view statement. So what you can see here, if you are familiar with Hive or SQL in general, it's just very similar to a create table as selected statement. You have all the options that you could expect when you create a Hive table, there are some differences. So for instance, when you create a view, by default it will be enabled for rewriting, but you can we have an option to disable that, and then you can specify, for instance, the storage handler that you want to use, some table properties, location, and so on. And the most important piece, that is the query that you want to materialize. So that's the syntax to create a materialized view with all the different options that we have right now. Now, if I give you a specific example, this is a very simple materialized view that is stored in Druid. So what we are doing here is creating a materialized view called Druid wiki env. We specify the storage handler, and then we just specify a very simple query that will read some data from the table source and will do some projections. And that's it. Your materialized view will be created and available in the system. There are other operations for the materialized view management right now. So you can drop a materialized view previously created. You can show the materialized views in the system, and you can filter them using some patterns. And you can also describe, use the describe option. This is also in Hive. It's to get the details about the materialized view, such as, I don't know, the size, where it's located, storage handler that it uses, so on and so forth. So more operations will be added in the future, and yeah, existing ones maybe extended too. Okay, so let's move to the probably the most interesting part, that is the materialized view-based query rewriting. So, I mean, the goal of the rewriting is just to automatically rewrite incoming queries using the materialized views without any other interaction by the user. So what the optimizer, this is done at the logical level, what the optimizer will do is that it will exploit the materialized view definition semantics. This is built on the ideas that are part of that paper. If you are curious to go more into detail, and the rewriting itself is implemented in Calcite. It supports queries containing table scan, project, filter, join, and aggregate operators. It includes in Hive some extensions over the original paper. In particular, for instance, we are able to generate additional rewritings without needing to do join permutation. So this is important in order to kind of scale the rewriting algorithm when you have queries that have a large number of joins. We also have the possibility to create partial rewritings using union operators. So what this means is that, for instance, if part of the query can be answered from the view, but some other part, you will have to maybe execute it from the source tables. The rewriting algorithm is capable of doing this kind of compensation, and to answer the query using the materialized view. More information about the rewriting coverage with some examples can be seen in that website that is part of the Apache Calcite project. Now, how does it? I mean, some important properties to enable materialized view rewriting. So there is a global property to enable and disable it in Hive. By default, I think, by default it will be enabled. Then a user can also selectively use enable, disable materialized views for rewriting. So when you create it by default, a materialized view will be enabled for the rewriting, but you can use this alter materialized view statement, and maybe you want to disable for some reason, you want to do some testing, anything, right? So yeah, you can control this kind of things with these properties. So let me show you some examples. These are just to highlight some of the features of the rewriting itself. So let's start with a simple one. You have in your database with two tables, employees and departments, and you have an application that is going to query about details about employees that were hired after 2016. So you know that that's what you will be interested in. So you can create a materialized view where you are joining the employees with the departments. And then you can see in the filter that we only take those employees that were hired after 2016. And below there, you can see, for instance, a query that can come afterwards, right? Where the query is asking only for the employees that were hired first quarter of 2018. What I show on the right side is the materialized view rewriting. So as I said, it works at the logical level. But yeah, here in the slides, I'm showing it as SQL because I think it will be easier for everyone to read it this way. So this is the equivalent SQL to the rewriting that we would produce. That is basically a scan over the materialized view. And you can see that we introduce the compensation predicate to filter only the rows that we need. So if the materialized view contents are the ones that you see below these 5 rows, then you would filter the rows and you would only obtain 2 of them that are the employees that were hired in the last quarter. So that's, I mean, what I try to show with this one is we have the capability of checking containment in the filter conditions and adding this kind of compensation predicates on top of the views. So the second example is a little bit more complex. So the schema is shown in the upper right part. So you have this is a typical star schema. It's based on the SSB benchmark. So you have a fact table, line order, and 4-dimension tables, part, supplier, customer, and dates. And let's assume that you are gonna run queries over this database, and you create this materialized view that basically what it does is just denormalizing this schema. So you will join line order with each of the rest of the tables and doing some projection on top. Now, when the query comes, for instance, that query filters by year and by discount, but only, filters by year and discount, yeah, only joins 2 of the original tables, not the 5 that are stored in the materialized view, and then it does some aggregation on top. So the rewriting can also exploit a feature that was included in Hive 3.0, that is the declaration of SQL integrity constraints. So you can exploit the SQL, in this case the PKFK relationship and the not null constraint in order to produce this rewriting, because you know that basically the materialized view preserves all the rows that were in the original table. So what you do is just scan over the materialized view, you apply the filters, and then you do the aggregation on top. So yeah, that's the second example. And finally, third example, more oriented towards, for instance, Druid. So imagine that you have this single table, in this case, a wiki table with some events, for instance, taken from Wikipedia, where you store basically when a page was edited and how many characters were added and how many characters were removed. And now you create this materialized view where you're basically rolling up by minute, because you know that you will not be interested in any data at a lower granularity than the minute. You know that, so you create your materialized view where you are basically floating the time to minute. Yeah, and then a query comes, and the query does some aggregation. You want the number of characters that were added by month, basically. So what you can see here in the rewriting is that that we will basically roll up on top of the materialized view. We will roll up on the time on the floor time to minute. We roll it up to floor to month, and yeah, and we do some aggregation. So what we show here basically is that we have also the capability to roll up, and especially to roll up on time dimension, which is also it's a very common use case, for instance, when you use Druid and using events. Now, what about the materialized view maintenance? Right now, in our implementation, the rebuild needs to be triggered manually by the user. So the user will have to execute that statement, alter materialized view, materialized view name rebuild. And we have support for incremental view maintenance. So what this means basically is that you only refresh the data depending on the new data that was added to the tables or on the data that was edited in the table. And this has multiple benefits. One of them is obviously that you decrease the rebuild execution time because you don't have to do a full rebuild. But it also has some kind of cool side effects. For instance, with LLAP, that is that it will preserve the LLAP cache for the data that was already existing in the materialized view. So you will only basically have to cache back only the new data that was added to the view. In order to support incremental view maintenance, though, the materialized view should only use transactional tables because that's either micromanaged that are insert only or full ACID. And this is because we need that information in order to know what actually changed in the source tables. And yeah, current implementation only supports incremental rebuild for insert operations, but and you know, for update and delete, basically what we do is that we will go back to a full rebuild. But yeah, we are working on supporting those operations too. Yeah, I mean, and the last line is just the rebuild will never fail. We will always attempt incremental rebuild. If we cannot do it, it will fall back to full rebuild. That is basically like an insert override using the materialized view definition. And now about the algorithm itself. So it's kind of cool that it relies on the materialized view rewriting algorithm itself. So how it works is that the materialized view stores grad IDs for the tables when it is created or refreshed. And this grad ID, what it does is that it will associate a certain row with a transaction, right? So then when the rebuild is triggered, you can just insert filter conditions on top of these tables. And then you can trigger that basically what will say is, okay, read only the new rows from the source tables because we have that information. And then you trigger the materialized view rewriting, and because we can check kind of the containment, then you know the rewriting itself will do the work for us. So how this works is that we will rewrite it into an insert override with a union where you union the data from the materialized view and the data from the new data from the source tables. Then this insert override, we transform it into an insert if the materialized view is table scan filter project join. If the materialized view has an aggregate, this is equivalent to a merge operation because I will show it in the next slides. You may need to update some of the records or insert new records into the materialized view. So let me show it with an example. So assume that you have this materialized view, and it's an aggregate one, and you are grouping by page user and doing some aggregations on top. So now the contents are over there on the right upper side, and the contents of the table, of the wiki table, and the contents of the materialized view are below. And then you have two new records that come in with the grad ID 10,000. Now you execute your alter materialized view rebuild, and what happens underneath is that in the first step, you transform that into an insert override over the view, where you have on one side, you can see that you are scanning the contents from the view in the union. On the other side, you are scanning only the new content from the original table. And then you are rolling up, because you need to roll up in order to insert it into the materialized view. Then the second step is that once you have this rewriting that is generated by the materialized view rewriting algorithm, you will transform this into a merge statement, where you basically say, okay, I will take the contents from the new contents from the table. If there is a match, I will update the row. If there is no match, I just need to insert the new row. Oh, I went too quickly. So what happens here is that the first row was existing, so it will be updated, and the second one didn't exist, so it will be a new row in the materialized view. So that's how the system works internally. Now, what about the life cycle? So this means what happens when the materialized view basically gets outdated, right? So by default, we do not accept stale data. This is the configuration by default. So this means that if the content of the materialized view is not fresh, we will not use it for automatic query rewriting. It is still possible to trigger partial rewritings that read both the stale data in the materialized view and the new data from source tables in the same way that I was mentioning about the rebuild operation. But we don't do this by default, just in order to kind of have more predictability for the system. Now, the other option that we also allow is to accept stale data if the user is OK with this. And how this is done is by defining the freshness of the data as a time parameter. So this means that if the materialized view was not rebuilt for a certain time period that you can specify in a property, and there were changes in the base table, you will ignore this materialized view. You will not use it. So you can set this property time window to, for instance, to 10 minutes. It can be also overridden, so you can kind of control it for at a lower granularity for each of the views. So you can also pass this property as a table property for the view if you want to play with this value depending on the materialized view. And then what you can do is to trigger periodically a rebuild operation, for instance, every 5 minutes. So that will give you certain guarantees that the view is not going to be outdated anytime by more than 10 minutes. So with that, I mean, I finished with what we have in Hive 3.0. So what about the road ahead? So there are some improvements that will be coming shortly for the current implementation. One of them that we need to work on now that we have all this, we have released all this new stuff is studying the performance and scalability, studying how an algorithm will react to many materialized views or single materialized views that are rather complex, and so on. One also important feature that we want to include shortly is the control the physical distribution of the data in the materialized view. So this is not implemented right now. So you want to partition your data, distribute it, sort it, cluster by. So that we will be including it. And also increasing the incremental V maintenance coverage. So as I mentioned, once you have updates or delete operations on the source tables, you will go back to the full rebuild. So we also want to support this for the incremental V maintenance. And then in the longer term, we would also like to implement materialized view recommender. We think that will be really useful so users do not have to look for those views that they should be materializing and so on. And that would be, we think, very cool. So that's all I have. Thank you for coming. Questions? Yeah.
Set it where you can run a specific time every day on a low network time,
So I mean, right now, when I was mentioning like running it periodically, right now this is not controlled from within Hive. This needs to be run, like for instance, with a cron job or whatever. So yeah, I mean, right now this is external to Hive. So you will have to kind of do this yourself. Yeah, this is something that we want to do, but Hive doesn't have, I think, support right now for this kind of periodic execution. I mean, generic enough. It has, for instance, you can do compaction every X, things like this, but it's not generic to add the rebuilder right now. But yeah, it's something that we are planning to do. Right now, you have to do it from outside Hive. Yeah. Yeah, that also works. Yeah. No. It doesn't require LLAP. It works better if you have LLAP, but it doesn't require LLAP, yeah. I mean, Even the views themselves, like I described, although maybe I didn't show many examples with it, but they can be stored, for instance, in Druid. So there is no need really for LLAP. Yeah. Yeah. No. So the question is whether when the views are revealed, whether they are unusable. No, they are still usable. So what happens there is that so while you are rebuilding the view, you will be like creating this new data, and at some point you will like you will flip, and then it will be available. I mean, the view will be refreshed, but the view is still queryable. That's why if you, for instance, set this time window to a certain time, you can still query it, and then at some point your data, moves, and then it's up to date. Yeah, correct. There is no downtime. Yeah. Yeah, behind. Yeah.
Yeah. So can you only use this reliably with ACID tables because of not being able to detect changes on the others?
Correct.
And materialized views themselves have to be ACID tables?
Yeah. So, first, yeah. So, I mean, the first question is I mean, when you say reliable, I guess what you mean is to detect changes in the source tables, right? Yeah. So, if you use tables right now that are not in the source tables, I'm talking right now. If you use tables that are not ACID or micromanaged, okay, so they are not transactional, in order to trigger the rewriting, we ask you to set this time window property to -1. That is, just execute the rewriting. Do not check for anything. Because we don't have the capacity to check whether something has changed in the original tables or not. Maybe we could do this, by the way. You will still need to set up like kind of a time window because you will not have warranties, but maybe we could do this with Hive has these events. So maybe you could kind of have certain warranties, but that this warranty cannot be too small because you may not meet it, but maybe something like that could be done. But right now what we do is that you have to set that parameter to -1 in order to trigger the rewriting. And the second question was whether you can store this, I mean, whether you can use this with other tables that are not, I mean, the materialized view can be backed by other tables that are not Hive tables. So this can be done. But for instance, the incremental, right now at least, the incremental maintenance, for instance, when you have an aggregate operator, it will not work. You will automatically go to the full rebuild option. But yes, you can. I mean, one of the tests that we have been doing is backed by Druid. So that's, yeah.
And how does the sync between Druid and another table when you're using Druid?
So you mean from Hive? Like, I mean, what do you mean from Druid and other? So how it works, I don't know if, can you say a bit what you mean with the question? I mean, because Hive can talk to Druid. You have the Druid storage handler. So I don't know if that's the, yeah, correct. So Hive has the possibility, it can talk to Druid via this Druid storage handler. So it has two options. I mean, you can create a normal table using the Druid storage handler. In that case, you have two options. One is that the Druid already, the table already, or the data source already existed in Druid. In that case, it's like discovery of the data source. You can also index data from Hive into Druid directly. And that's like a Hive table that is backed by Druid. For the views, it's similar to the Hive table backed by Druid. So you are basically inserting the data from Hive into Druid, and then you expose it to Hive as a materialized view. Yeah, so this is, the integration is there. So it could be used also with other storage handlers. It's just that Druid is, I mean, is very good for this kind of workloads, yeah. So, you have a... Yeah. So the first question, you don't have to do anything. When you mentioned analyze, I thought you were maybe talking about the stats or something like this. So you don't have to to do anything, the rewriting will be triggered automatically. One thing that we are thinking about doing, but we don't know if we will do it or not, is that you can maybe hint a certain materialized view for the when you execute a query. Maybe you can hint it and you can try only with this view. But right now you cannot do this, and what you try is with the views. There is some pre-filtering, but yeah, with the views that will be in the system. Second question, I'm sorry. Yeah, the query plan will show the materialized view. So the plan will be, you will see like a table scan on top of a materialized view. Yeah, and then whatever computation you have on top. Yeah. So when you do explain plan, you will see it. Okay, thank you very much.